So today we are welcoming our speaker, Dr. Benjamin Hsiao, who is the chairman and CTO of SWFTLabs. He's also a distinguished professor of Stony Brook University and has a whole list of other accolades I could get into, but without further ado, I'd like him to share his screen and start the presentation.
Well, thank you for the council for inviting me. And so when I started with this project, I was working on plastics. Then I realized that nature's actually make a lot more plastic, or we call this polymers, than synthetic polymers. But we really not utilize them enough. And current chemistry technology will allow us really to rethink whether we need to make more synthetic ones or just take advantage of nature's polymers. That's the starting point. Specifically, I was interested in some nanostructure fibers. And what I'm showing you here is a tree. You can actually analyze every part of the tree. You can start breaking them down to a very small nanoscale fibers level. And the reason I was interested in this, because I was at that point, I was interested in making filters, like papers filters, but made of nanofibers, so I can remove very small contaminants using lowest pressure available, that's gravity, to remove contaminant. So at that point, I was just looking at different technology to make this nanoscale fibers. So this is a table. I spent about a year in Sweden and learning how to make this nanoscale cellulose, or people call it nanocellulose. So there's three different types. There's a CNC, stands for cellulose nanocrystals. CNF stands for cellulose nanofibers. They both are processed from top-down approach. You take a tree, you do chemistry on it, and you are introducing some chemical group. Usually they are charged. And denomination is a mechanical ways to actually break them apart. And there's another process called BNC. It's a bacterial nanocellulose. Actually, we use them quite often. We can actually use them as a food additives or even a moisture facial mask to remove wrinkles. And made of a juice, they use bacteria to actually make this nanofibers. And I wasn't quite interested in BNC because I thought this nature already had plenty of biomass. I can extract these nanofibers. So I don't want to bore you with the chemistry, but I highlighted this burgundy color ones, the tempo treatment. Tempo is a chemical treatment. And I want to highlight this very low energy demand. Because to process then, higher energy means more expensive. And very low energy means very easy to make nanofibers. So again, this is a fancy chemistry plot. And I don't expect you to understand this, but I want you to know that if this little block is cellulose nanofibers, what we have, this tempo chemistry will do is it will turn one group into a charge group. COONA, Na is sodium. It's like a salt. Salt dissolved into water, it gets dissolved, it becomes charged. So it's negatively charged. Negatively charged property is very important because if the fibers, they're charged, they will try to repel each other. So that's the reason that you don't need too much energy. They were just very easily defibrillated. So I was intrigued by this charge because if I have charged materials, I can also absorb or remove heavy metal ions in the contaminated water, like lead. So I was very intrigued. But then this chemistry, although very, very elegant, if even you're not a chemist, you know all those chemicals are very exotic. And exotic means that if I'm going to process all those available nature polymers, I'm going to deal with the recycling of these chemicals, reuse, purify them. It's just not a sustainable or not an environmentally friendly process. So fast forward, so we developed this closed reactor system. So we can use a wide range of inputs, and we get two types of outputs. One is the liquid, one is the solid. So the whole process is very much like cooking a vegetable soup. You start with your ingredients or feedstock, and you cook them into water. After a few hours, all the nutrients get extracted and fused into the liquid part. And that's one, the remaining part is this pulp. And the pulp, it turned out to be charged if you use nitric acid to replace water. Of course, we cannot eat this soup, but plants can. So this becomes a zero waste process. It's a closed loop reactor or cooking system, if you wish. So outcome, this low cost fertilizers because they extract all the nutrients back from the feedstock. And you can make this negatively charged nanocellulose, and that leads to the beginning of making a gel, like gelatin. Because if they charged, you can use a micronutrients to actually to hold them together, become gelatin. You can also, there's just a wide range of application with this gelable material. So currently, and at the university, we have received several funding from National Science Foundations. We actually, this is one process, we call this NOP 2.0 process. And the reactor is this stainless steel reactor, and it can be scaled up. This is 50 liters, and you can scale up to 500 liters, even bigger. And all the pump controllers, they're capable of driving very large scale reactors. So in our view, that food scale processing equipments will be very much like a brewery or wineries and large and reactors. And the temperature is not very high. It's only 50 degrees C or so. Everything is contained. So even though you use nitric acid, which is not very concentrated condition, that you can do this NOP reaction. And outcome with the liquid and the suspension that contains solid. And it just happened that we also realized that non-woods is even a better feedstock source because non-woods and their structure, the cell structure is much looser. They also have less lignin content. They're very soft. Usually they're underutilized because they have less value than wood. And but they're perfect feedstock to extract this nanoscale fibers. So what I'm showing you here, just from agave to bamboo leaves, and they're much underutilized. You can use cut grass, shrubs, in any kinds of feedstock. And we had done, we had focused on agricultural residues because after harvest, and you have lots of residues left on the ground. We have tried sorghum, maize, beans, millet is specific part of sorghum, and you can always make this nanofibers. W means the width, L means the length. So they are really, really nanoscale scaffold, and they are also zeta potential is negative, means they're negatively charged. They're really wonderful materials for water purification at that point. So for example, we can remove lead, cadmium, uranium, you name it, and you add this suspension into, let's just focus on lead. Lead is 2 plus into water. And this is a lead solution. It's colorless. It's the same types of problems in Flint, Michigan. People drink lead contaminated water. You can add your suspension of negatively charged nanocellulose, and immediately they form this flocked or gel-like materials. And this is actually, it becomes another inspiration. We know we can gel these materials with metal ions. So 2 years ago, my group, we actually wrote a very, very comprehensive articles about using nanocellulose for a wide range of water purification. And if you look at the page number, it's close to 100 printed page. It's almost like a small booklet. And the chemical reviews is probably have the very high, one of the highest scientific impact factors for all the chemists to study this. So we can use a wide range of feedstock, either from raw or processed. Processed is like Amazon send you a cardboard box. You can take that box. You can use that as a feedstock too, and using our NOP. And for a wide range of water purification to make membranes like filter papers. And because the fiber is very small, so you can remove very, very small contaminants. You can coagulate, then you can do use absorption, or you can even embed photocatalyst nanoparticles for a wide range of applications. But then we receive another NSF grant. We decide to broaden our feedstock. We decide to include protein as well as a wide range of, for example, manures, animal waste. And what we have found is something is better to make biogels like cotton gin, jute, palm tree, bagasse. After you process sugar cane, the leftover is called bagasse, even trees. Something is very good for fertilizer, not much gels. Like chicken manure, for example, food waste, protein can also be extracted into a safe fertilizers, because nitric acid will even take your degraded food and it degrades harmful pathogens. So pathogen itself, it becomes a feedstock. So and we have done extensive safety study and find out this actually NOP process is quite powerful. It dissolves almost everything except cellulose, or of course minerals, and rocks, for example, sand. We cannot dissolve that. So we also know that the NOP, the nanocellulose, if we cross-link them, make them into gel using micronutrients, like magnesiums or calcium, we can actually make them into a growing medium. So left one is actually just pure gel to grow lettuce. The right one is the peat moss. And the middle one is we actually try to come up with a substrate to replace peat moss because peat moss is a very good growing medium, but it's not sustainable because if you are a grower, you will know that peat, you need to mine them, and that's not a sustainable operation to build the peat mine. You probably need 1,000 years to actually develop this peat bog. So we have also done a very preliminary technical economic analysis and find out how expensive are they? Are they have any commercial values? So we found that if NOP recover fertilizers, because they're very local, they can be 20% cheaper than synthetic fertilizers. For growing medium, they will be 60% cheaper than peat moss. We can also use these materials to improve the soil health because we can retain the water. They are 30% cheaper than commercial ones. They're a lot cheaper than synthetic plastic hydrogels, and they impose no environmental uh, 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 effect because they're really made of degradable cellulose, so they're completely environmentally friendly. So I know Council is very into is promoting composting. We think composting is wonderful. And NOP is not competing with composting, it's actually trying to complement it. And so NOP versus composting, NOP is quite clean and safer and takes a very short time because it's really like cooking. And composting just more land intensive and takes a little bit longer time. Anytime it takes longer time, that means you need more land. And that's really a problem for Long Island too. We're running out of land for large scale composting. So this is just another presentation to compare the two. I think they're really good complementary systems. There are many, many case composting, just wonderful. But NOP perhaps can process some of the, to start with, more biohazardous waste. It's probably better with NOP. And it both will do a full nutrient recovery for safety, for soil safe, and human safe. NOP is completely safe. And there's no odor at all. If I show you a biogel made of cow manure, you would not know that's from cow manure. And no smell, and it's completely safe. And the speed takes hours. So this is almost in and out the next day. You can get it. So, this is try to convince the National Science Foundation to continue the funding of this. So today, I think the world has a less fertile land to grow crops and more people to feed. And the current farming practice, and as we all agree, represents a broken loop from making fertilizers to actually apply these fertilizers, and crops only take a very small part of the fertilizer, and then we only eat a very small part of the food. Even with the food, the council recognizes there's tremendous food waste. I think our technology can perhaps close this nutrient loop. And synthetic fertilizers, we can talk to farmers, growers. It really becomes more and more expensive, and they're also become less environmentally sustainable because all the nitrogen runoff. And I have to admit, when my mother tried to grow some crops in my backyard, we get fertilizer for her. I know there are lots of runoff just by apply fertilizer in the beginning. And also impact of climate change just make this problem even worse. There's drought, and there's also flood. After the flood, you have to regrow them, and all the nutrients get run off. You're gonna need more fertilizers. When you have droughts, all the crops die, and you have to irrigate the land again. So, and we really spent lots of effort try to keep our soils healthy, and it's always a losing battle, it seems to be. And most nutrients are lost by fertilizer runoff or get left behind in agricultural residues or animal and food waste. And talk about the scale of the waste. The 3 billion tons of agricultural residue every year globally. Animal waste is even worse, 5 billion tons, because I love my dairy products. And cows really making a lot of waste, for example. And food waste. Food waste, in terms of the value, globally, 1/3 of food is wasted. But in the US alone, it's about $161 billion waste. Plus, you have to remove them and compost them. So it's a crisis, but it's a Chinese word for crisis. It have two words, right? The first one is the danger, followed by an opportunities. I think we really have some good opportunities here. And NOP probably can allow us to close this broken nutrient loop because it's a zero waste process that can upcycle this natural organic waste. And we can develop some new farming products that like growing medium, soil amendments, or biogels. And more than that, the technology can really reverse desertification, can really have the power to turn deserts back to oases. And on Long Island, we can also think about ways to grow vegetation to enhance coastal resilience, because we have a very sandy land on Long Island. Every time there's a storm, if you have a beach front house, you start losing your front, and because the sand cannot hold the structure. But if we can grow vegetation on the sandy bluff, we can enhance the coastal resilience. And that's where we start with the SWFTLabs. And I want to give you an overview in our current focus, where we're gonna go from here. And SWFTLabs really established probably 2019, but we're really unfortunate that we hit the COVID. So immediately we stayed dormant for about 2.5 years. And it got relaunched in 2022. We tried to pioneer this natural oxidation process and to convert agricultural waste, food, beverage waste, animal waste into two highly valuable products. One is this biogel, one is the biofertilizer. And this is my group. And in the back, this is the CEO, Ryan McGann. So at the end, I'm gonna list his contact information. If you're interested in helping this startup company, you can contact Ryan. So progress to today, we really spent about 10 years on this project. We probably over $7 million R&D fund from the government, and it's time to pay back to help the community. So we have already established some activities and facility from lab scale to small commercial scale. And we also have established an IP portfolio with 8 patents and applications, and counting more coming. And we're working on a wide range of feedstock, including food waste and brewery waste and animal waste. And of course, we can go many directions. We try to focus to demonstrate a lower hanging fruits, initial wins, so we can become sustainable. We are working on ongoing growth trials. I know Francesca is being involved in some of the growth trials to help us. So fertilizer part, of course, we can have liquid fertilizers. We can also dry them into granular fertilizer. This fertilizer is different than synthetic fertilizers because they're recycled from the plant biomass or waste. So they have lots of carbon there. Because of that, they're a little bit slower release, which is actually useful for plants. If the land is really dry and you apply this gel and you water them, they can hold the water. So it's a very good wetting agent. It's water holding agent too. And they can rebuild the soil health, and they're completely biodegradable. And we can also, because the materials itself is a good water purification materials, we can actually capture the agricultural runoff, all the nitrogen runoff. We can recapture them and reuse them. We can coat the seed with the hydrogel so they can keep the seed moist and can withstand drought. And they're very, very good for hydroponic farming, growing media. And that's currently working on it. We can even engineer a new substrate like a peat alternative. We can use wood fibers to make peat. We don't have to import peat anymore. We can even use this spent peat substrate and recondition them back to the fresh one. And we also are working on 3 non-agriculture applications like erosion controls, reverse desiccation, and the water remediation process. But to start, we're really focused on SWFTLabs' first application in the agriculture part. So this is just some cartoons, see how it will work. So currently we're working with a dairy farm lately in Holland. They have a small robot. They try to collect all the manures, and we're actually working with them to take the facility is really state of the art, very clean, except they do not know how to deal with their collected manure. So we try to work with them and see if we can process this manure to help them to actually make them into fertilizer and gels to grow grass back again to feed the cows. So it becomes a circular solution. And this is just the one way proposed to them. You have a hydrogel pump. You can spray them. You can hydro seed them, and you can grow the grass back. We are actually currently also working locally with some golf course by taking wood waste from the compost and see if we can convert that back to fertilizers and the hydrogel to help golf course to reduce their synthetic fertilizer use and use our materials. And so the process, currently we have two types of projects going on. One is centralized processing. We can have a large plant, which is really like a small brewery, if you wish. We can truck the food waste, agricultural waste, yard waste, brewery waste, etc., to there, and out come biogels, biofertilizer. Or we can develop a mobile systems. We can take this small mobile system to the farms, grocery store, small landfills, waste management facility, and food processing facility, and just try it and try to optimize the system. I think two are completely complementary to each other. So our business model, it really depends on the local need in terms of farming, from large-scale agriculture to specialty crops and horticulture. And we can have a hybrid between centralized facility or the local facility. And currently, we're really working with a dairy farm and mostly some waste management facility, as well as horticulture farmers, and see which business will be shall we go after first.
All right, I think we had some great questions in the chat from earlier. So let's see.
Mark's question is whether this process could pour PFAS out of water and soil. NOP can generate absorbent to absorb PFAS. That's yes. We actually working with the Center for Clean Water Technology at Stony Brook University. We actually are developing a absorbent to remove PFAS. We cannot destroy PFAS, right, unfortunately, but we can remove them from water for drinking, remove them from the soil, so the plant's not going to uptake PFAS into the crops.
Thank you, Ben.
Yeah. Fibers from bamboo are used to make threads for clothing. Yeah, we can use any biomass and to make this nanofibers, and bamboos are wonderful. Hemp is wonderful too. Actually, we have some cannabis farmer ask us whether we can help them process their residues. And yes, we can do all that. It is a platform technology, and I'm not a businessman. And Ryan kept telling me, platform technology, you need to focus. Which one is it makes sense in terms of business model? So we are trying to still focus on the early win.
All right. Mark also said he sees NOP as possibly the perfect alternative to anaerobic digesters.
I would think so. But anaerobic digester is about a few years ahead of us, and many people already invested large facilities, and we're just about to take off. And so I think if you allowed us to have 2 years, and at that time, once the technology being demonstrated at a larger scale, yes, potentially can compete, even displace the digester technology. But I think at the end, but the facility investment is more. And for us, we can probably afford it, but for some people, they cannot afford it. Digesters lots cheaper. So two are really complementary. And hate to say this will replace anything, but will complement, including composting as well.
Absolutely. I think all applications have their own right and their own importance in the system overall. So that's great.
Yeah,
I just added my 2 cents.
I
So
saw Yolanda say 500 liters is nothing, which I agree. One step at a time. We just learn how to stand up to walk, and the next thing, if we have enough funding, we'll probably generate 10 of the 500 liters and reactor for one facility. And I think that's really scalable system. You know, my analogy is like a small brewery versus large scale brewery. Right, think about the grasses. Yeah, grasses a lot. So certain things are worthwhile for composting. Certain thing is probably more suitable for NOP reaction. And I think cow manure is perfect because what do you do with cow manure? Lots of them. And I think biohazardous materials, hard to compost, probably should start with the NOP first. And if you're interested in the speed to process the food waste, because the acreage is smaller, maybe that's also makes sense. So we are just learning at what scale, what time frame, which process will make more sense. I think hopefully by in 2-3 years, you have different technology to handle all the waste. You have composting, you have a digester, you have NOP systems. The most hazardous materials go to NOP, something less hazardous but still quicker to degrade go to a digester, and something that's totally harmless, wood chips, you just use the composting. I think that's probably gonna play it off, because once you start mixing it, then composting becomes very smelled, becomes not safe. Okay. Same question. Source of the nitric acid. And what is nitric acid made of? From petroleum products. Yes, they are made of petroleum products. Nitric acid start with ammonia. So it's from ammonia convert to nitric acid. It's very straightforward process. To make the ammonia, if you're not much chemist, you know the chemical structure is NH3. So we have a lot of nitrogen in air, right? So air have lots of nitrogen, but don't have too much hydrogen. So you have to make hydrogen. And right now, the way to make hydrogen is really use petroleum-based process to make hydrogen. And although right now we're moving towards green hydrogen, if you can use water splitting to make hydrogen without generating CO2, and then you have clean hydrogen, that's going to be 5-10 years away. Then you have green ammonia. Then you have green nitric acid. And so nitric acid is necessary for farming. It doesn't matter you make it green or blue or gray. And the source of nitric acid, we are talking to large fertilizer companies, and they're making a lot of ammonia and nitric acid. Nitric acid is also the essential ingredients to make nitrates, like the one that you buy in Home Depot, the nitrates, or nitrogen fertilizers. So we are directly also working with large-scale fertilizer company, and they for them, if they supply nitric acid, they actually gonna get more nutrients out. So they use less nitric acid, more nutrients. So for them, the products will be less ingredients, more more value. So they're very, very interested.
I just have one other question from Quillian in the chat.
Yeah,
Is it possible to surpass the 500-liter reactor size when using NOP?
yeah, it is possible. And I'm just use the 500 liter as uh, it's just a benchmark. Of course, you can design bigger. And I think once you become bigger, I think the safety, environmental health and safety evaluation come into play. You have to also evaluate the risk with the large scale versus the smaller scale. How do you manage the risk? And the question is always the brewery, and you want to make a huge brewery, very large tank, and heating, cooling becomes problem. The reaction is not so homogeneous versus something that you get more homogeneous reaction. We're going to evaluate that. And I don't think that's a problem. You can have modules designed, many of them.